vast session of our course. During this course, I try to give a brief introduction to topological semantics of modal logic. We start by studying the quirky semantics of modal logic, and then we consider the topological semantics of modal logic. As we said, there are two kinds of, topological interpretation for modal diamond, as McKinsey and Tarski introduced. The one which is called c-semantic in some literature consider the interpret the modal operator diamond as the closure operator, and the other one, which is called d-semantic in some literature, interpret modal diamond as the derivative operator. So in c-semantics, we have that diamond of phi is true in X if and only if X is in closure of phi, where this set is the set of all points such that phi is true in them. So it means that you can say that if and only for any open set U, if X is in U, then there exists some point Y in U such that phi is true in Y. And for box operator in c-semantic, I mentioned C in here to emphasize that I'm talking about c-semantics. If and only if X is in interior of phi, or in other words, there exists some U in tau such that X is in U, and for all Y in U, phi is true in Y. It's a c-semantic, we talked about that, and yesterday we started to talk about d-semantics. Let's review the basic definition. As we said that a point X is a limit point if for limit point of a subset A, if every neighborhood of X contains a point in A which is not equal to X, and we denote the set of all limit points of A by d of A. And we said that we have these properties for the derivative operator. The set of limit points of the empty set is the empty. If A is a subset of B, then d of A is a subset of d of B. D of A is a subset of d of A union A, and d of A union B is equal to d of A union d of B. And we have a co-derivative operator which defined as the complement of the derivative of the complement of A. Then we said that in this semantic, we have that M and X satisfies diamond of phi if and only if X is in D of phi, which means that for any U, if X is in U, then there exists some point Y in U such that Y is not equal to X, and in Y phi is true. Then by duality of box and diamond, we have that box is true in X if and only if X is in T of phi, which means that there exists some U where X is in U and for all y in u, for all y in u, if y is not equal to x, then y satisfies phi. So you can see that the difference between the c-semantics and d-semantics, in c-semantics, for example, for diamond, we just need to have one point in neighborhood of x where phi is true, but in d-semantics, we need that this point is not equal to x. So the main difference between these two semantics is that. So we saw that these axioms are not valid in the class of topological semantics when we consider derivative semantics, and this axiom is valid, which says that P and box P then box of phi, and we said that we add this axiom to K. Note that for c-semantic, we know that S4 is the logic of all topological spaces, where S4 is K plus T plus 4, where T is the axiom phi, then diamond of phi, or equivalently we can say box of phi, then phi, and 4 is the axiom diamond of phi, then diamond of phi, or equivalently box of phi, then box of phi. But in here I have version which is weaker than 4. It says that instead of having a box of phi, then box of phi, we have phi and box of phi, then box of phi. And we saw that we can have a translation from modal formula to modal formula in a way that we can have a formula in a way that we can have this lemma which says that a formula phi is valid in x, c valid in x, if and only if its translation is d valid in x. And we can prove that phi is a theorem of S4 if and only if its translation is a theorem of WK. For in this translation, we just, in the box version, for example, we have to add phi and box of phi, because it's clear from the difference between these two axioms that we have defined our translation in this way. So as we saw in c-semantics, for proving the completeness for topological spaces, we use the completeness results in quickie semantics and then transfer the results there to some results in topological semantics. Here we want to do something like that. So first we have to know that for which class of cube key frames we have a completeness for WK4. So as we said, axiom 4 is valid in the class of cube key frames where the relation is transitive. This axiom is weaker than the axiom 4, and if we check, we can see that this axiom is valid in the class of cube key frames where the relation is weakly transitive. By weakly transitive, we mean that we have these properties for all W, V, and Z. If we have W R V and V R Z and W are not equal to Z, then we have W R For transitivity, we have for all W, V, and Z, W R V and V R Z implies that W R Z. So if we have such condition in our frame, if our frame is transitive, then we should have some loop over W. But if our frame is weak transitive, we do not need to have such a loop. And it's proved that WK4 is sound and complete with respect to the class of all weakly transitive frames. And also it's proved that WK4 is complete with respect to finite rooted irreflexive WK4 frames. And we said that how we can make our frame irreflexive. We need to duplicate reflexive points. Another point was that in c-semantic, for any frame F which is reflexive and transitive, from any such frame we can have a topological space by defining the offset topology. And we saw that if M is any model over such frame, then if we consider a model over a topological space constructed from F by the same evaluation, then for any point X in X, we have that phi is true in the point X if and only phi is true in X when we have a topological model. So the satisfaction remains same if we have we saw our model as a QQ model, or we see it as a topological model. Here we want to have such notions. For any given WK4 frame F, we consider F bar, which is reflexive closure of F. And then we construct a topology over F. Note that if I want to define a offset topology over F, I want to say that the offset topology over F is the same as the offset topology over F bar. So when we consider the offset topology over F, it cannot consider which point was reflexive or which one it was not reflexive. We saw this lemma yesterday, and as we said, in c-semantic, for any given frame F which was reflexive and transitive, For any topological space X, we can define a relation, I called it RC, or R tau, which we called it a specialization order, and defines as follows. X is related to Y if and only if X is in closure of Y. And we saw that if X is an Alexandrov space, a space which is closed on the arbitrary intersection, then X and R tau is reflexive transitive frame. Now we can define another relation over X. We can define the relation RD and say that X is related to Y by R of D if and only if X is in D of Y. In this case, X and R of D form an irreflexive WK4 frame. By WK4, I mean weak transitive frame. And we saw that there is a one-to-one correspondence between the class of Alexandrov topological spaces, the class of reflexive and transitive relations on X, and irreflexive and weakly transitive relations on X. So by this theorem, we can show that WK4 is the D-logic of all topological spaces. To prove this theorem, we use the completeness of WK4 with respect to irreflexive weak transitive frames, when in this case, if phi is not a theorem of WK4, if phi is not a theorem of WK4, then there exists a frame F or a model M which is irreflexive weak transitive model, and there exists some point X in M such that M and X does not satisfy phi. Since our model is irreflexive and weakly transitive, we can construct a topological space over that, and then we can see that M, when we consider it as a topological space and the point by the same valuation, then in M and X, phi is not true. No, before going to give the other completeness result, let me to review the other notion which preserve the validity. We saw that in semantics we can define a function between two Kripke frames, which we call it bounded morphism, which preserve the validity. In topological c-semantics, we have a function which we called it interior map, which was a continuous and open map. Here we can have such a function which we called it a d-map, and it defines as follows: for any topological space x and y, f from x to y is a d-map if it's a interior map and is pointwise discrete. Interior map is an open and continuous map, and pointwise discrete is the condition that for any point f and point y in y, the f inverse of y is a discrete subspace of x. So to have a function which preserves validity between two topological space, preserve d-validity between two topological space, we have to add another condition to the interior map which preserve the validity c-validity between topological spaces. We have to add the pointwise discreteness as a new condition to f. If f has this condition, then it preserves the validity between formulas. Also, we can see that this condition, interior map and pointwise discrete, is equal to have this condition: f from x to y is a d-map if and only if for any subset a of y, f inverse of d of y is equal to dx of f inverse of a. By dy and dx, I mean the set of limit points in x with respect to topology over x, and d of y is a limit point in y with respect to topology over y. We can see that the condition of being interior and pointwise discrete is equal to have this condition. Then we can prove that the validity of formula is preserved by this notion. I mean that I can write this corollary in this way: if f is from x to y is a d-map, then for any formula phi, if phi is valid in x, then phi is valid in y too. Because by LD of x, I mean that the set of all formula phi where phi is valid on x. So this notion means that for any formula phi, if phi is valid in x, then phi is valid in y. Okay, as you saw, when we want to prove completeness in topological spaces, we try to transfer completeness result in cryptosemantics to topological semantics. So it's a good idea to be able to have a function which we define from a topological space to a WK4 frame. Note that if when we work with c-semantics, for any reflexive and transitive frame, we can just consider its topology over that, and then we can work by it easily. But here, because the topology over weakly transitive frame cannot distinguish between reflexive and irreflexive points, so we need to be able to manage these differences. Our function should be able to consider when the point is reflexive or the point is not reflexive. Or we have to make some completeness with respect to irreflexive frames. For example, for WK4, we said that WK4 is complete with respect to irreflexive weakly transitive frame. So we can transfer the completeness there to completeness to topological spaces. So we can define a function from a topological space X to a WK4 frame F in this way. First, F should be an interior map from X to F bar. F bar is the reflexive closure of F, and we can see it as an Alexandrov topological space. So we can consider F as an interior map from X to F bar. And then F should have two other conditions. The first one is called the irreflexively discrete, or I-discrete for short, which says that for each irreflexive point W, the set of F inverse of W is a discrete subspace of X, and the other condition is reflexively dense, or R-dense as a short, which says that for each reflexive W in W, F inverse of W is a dense in itself subspace of X, or in other words, F inverse of W is a subset of dx of F inverse of W. So our function can distinguish between reflexive point and irreflexive point. It has one condition for reflexive point and one condition for irreflexive point. Then we can prove that if F is a dimorphism from X to F, which is a surjective D-map from X to F, then D of X is a subset of L of F, which means that again I can write this corollary in this way. If F from X to F is a surjective D-map, then for any formula phi, if phi is valid on X, then phi is valid on F. If phi is D valid on X, then phi is valid on F as a Kripke array. Now let's consider some completeness result with respect to some special classes. The first class that we want to consider is the class of TD spaces. We said that a topological space X satisfies the TD separation axiom, or simply X is a TD space if for every point X there exists an open set U and a closed set F such that X is equal to the intersection of U and F. So the TD separation axiom says that for any point X, there should be one open set U and one closed set F such that the singleton X is equal to the intersection of this open and this closed set. The axiom is in between T0 and T1. Now I want to show that if X is TD space, let's first review the T0 axiom, which says that for any point X and Y, if X is not equal to Y, then there exists some open set U such that X is in U and Y is not in U, or Y is in U and X is not not in U. It's a T0 axiom, and T1 axiom says that for any x and y, if x is not equal to y, then there exists U such that x is in U and y is not in U. Now I want to show that if x is TD space, then x is T0 space. So I want to show that x is T0 space, so I have to consider two non-equal point and show that there exists one U with this condition. So suppose that x and y are 2 points in x, and x is not equal to y. Then, since our space is D space, then for x there exists an open U and a closed set F such that the singleton x is equal to U intersection with F. So since x is not equal to y, then x is not equal to y and the singleton x is equal to this intersection, then y is not in U or y is not in F. So if y is not in U, we have that so x is in U and y is not in U, or we have that x is in F and y is not in, and y is in x minus F, and x is not in x minus F. Since F is closed, this set is open. So for two non-equal point x and y, we have an open set U where contains x and not contain and doesn't contain y, or the other open set is x minus F, which does not contain x and contain y. So our space is T1 space. Another condition that we can prove for TD space is that the topological space is T if and only if D of A is a subset of D of A. Let's see the proof of that. First, note that a set A is closed if and only if the closure of A is a subset of A, which is equal to set that we know that closure of A is A union of D of A is a subset of A. A is a subset of A, so this means that D of A is a subset of A. So if D of A is a subset of D of A, then this means that D of A is a closed set. It's closed for every A as a subset of X. Also note that for any X in X, we always have X is not in D of X. So with the things that we said in above, D of X is closed and X minus D of X is open, and X is equal to X minus D of X intersection with closure of X. Then X is a TD space. So I want to show that X is TD space when we have the condition that D of A is a subset of D of A. I said that if we have the condition that D of A is a subset of D of A, this means that D of A is a closed subset for any A as a subset of X. And also for any given point X, we know that X is not in D of X. So it means that X is in the complement of this set. And D of X is a closed set. X is in, so X minus D of X is an open set. And X is in this open set intersection with this closed set. So X is a TD space. Now for the converse direction, I want to assume that X is TD space, and I want to show that for any subset A, D of A is subset of D of A. Conversely, we have to show that for any A as a subset of X, D of A is a subset of D of A. Now assume that X is not in D of A. So by the definition of the set of limit points, if X is not in D of A where there is a neighborhood, there is an open neighborhood U of X such that U minus X intersection with A is empty. Our space is TD space. So there are open set and closed set B and F. Such that X is equal to V intersection with F. U is a neighborhood of X. V contains X and is open, so the intersection is also an open neighborhood of X. Now we show that U intersection with V intersection with D of A is empty. Then if we show that, then we can conclude that X is not in D of A. So if X is not in here, X is not in here, which means that this set is a subset of this set. So now I want to show this. Suppose that there is some point in this intersection. We know that X is equal to V intersection with F, and Y is in here, so we can conclude that Y is not in F. So U intersection with V minus F is an open neighborhood of Y that has empty intersection with A, which is a contradiction. So X is not in D of A. So in closure of D of A, and since D of A is a subset of closure of A, So we have that if X is TT space, if and only D of A is a subset of D of A. Now by this proposition, we can see that for in topological space X is a TT space if and only if the axiom diamond of P, diamond P, then diamond P is valid over X. And as you remember, this axiom is the axiom for K4, which is K plus the axiom 4, which is diamond of phi, then diamond of phi, is the d-logic of all TD spaces. Let's put that. By the previous proposition, we know that D of A is a subset of D of A, for each A as a subset of X, we can obtain the soundness part. For the completeness, suppose that K4 phi is not the theorem of K4. But it results from cryptic semantics we know that there is a transitive frame F such that phi is not valid on now. If our frame is an irreflexive frame, then we can make the topological space over that and conclude that phi is not valid over that topological space. But it's possible that our frame is not necessarily reflexive and it contains some reflexive point. So we should handle these reflexive points and make our frame irreflexive in a way that the validity does not change. We do this in this way. Let G be a frame N with its order. Then consider F times G, which is a frame that its points contains, for example, if W is F is W and R, F times G is the set of all W and N when W is in W and N is in N. Then we can see that this frame is a transitive irreflexive frame, and also we can see that F is a bounded morphic image of F times G. So F times G does not satisfy, if so phi is not varied over F times G. By this method, as you may remember, for making a frame irreflexive, when we want to prove the completeness of WK4 for irreflexive frames, we duplicate reflexive point. In here, I mean, for this case, for handling the reflexive point, instead of duplicating point, we make an infinite version of any point. Then we can make our frame irreflexive. And then we can prove that by this result, thus K4 is complete with respect to irreflexive transitive frame. So since we have irreflexivity now, then we can make the completeness over topological spaces. Because the topological space which obtained from a transitive frame is a TD space. You can check it easily. So to prove the completeness of WK4, K4 over the class of TD space, first I prove that K4 is complete with respect to irreflexive transitive frame, and then from that I can get the result for completeness of K4 over topological TD spaces. Because as I said, we can easily show that if our frame is transitive, then the topology that it makes is a TD space. Another interesting result for K4 is the completeness of K4 with respect to stone spaces. As you know, stone spaces follows rules in duality between topological spaces and algebraic structures, between Boolean algebras and topological spaces. So a compact Hausdorff zero-dimensional space is called a stone space, and it's proved that K4 is sound and complete with respect to stone spaces. We don't have enough time to talk about that, but you can find it in a paper by Bijanishvili, Iseki, and Gabeleya. I If I remember the name of paper correctly, I think its name is that Modal Logic for Stone Spaces. You can find the proof and details in the paper, in that paper. As we said, by McKinsey and Tarski theorem, we know that S4 is C-complete with respect to the real line, with respect to the set contour set, or with respect to the rational line Q. Here, for d-semantic, as I said, since we have the expressive, more expressive power than c-semantic, we can have different logic for these spaces. For contour set and for rational line, we have the same logic, but we can have another, we have another logic for the set of real line. For a topological space X, we have that X that is diamond of 2 is valid on X if and only if d of X is equal to X, which means that X is dense in itself, which means that X does not have any isolated point. So if our space is, that this formula defines the class of spaces which does not have any isolated point. And we know that C and Q are dense in itself spaces, and also are TD spaces. So by some other details than we should do, we can prove that the d-logic of the contour set or the d-logic of the rational line, both of them are K for D, which is K for plus D axiom diamond true, which characterizes the class of dense in itself spaces. So here the d-logic of the contour set and the set of rational line are equal. But the d-logic of the set of real line is not equal to the d-logic of the contour set or rational line. For real line, first Shetman studied it, and then the topological semantics for real line is proved by him in another paper. We don't have enough time to talk about that because we have to add some more axioms to our logic. So I think now I try to give a brief review about d-semantics of d-semantics of modal logic. And now it's a good point to have a break. Okay, let's start the second part and the last part of this course. Now I'm going to talk about the provability logic GL. GL is a branch of modal logic where the modal operator box is interpreted as it's provable. So box of phi means that phi is provable in some formal system, which usually considered the system of piano arithmetic. If you don't know what is piano arithmetic, you can consider it as a first order theory of natural numbers, for example. GL is the logic which contains the basic normal model logic K, and also the axiom Lob, which is the axiom box of P, then P, then P, then box of P. Its axiom, which is named Lob because of his work in for probability logic, and also probability logic is called Godel-Lob probability logic. Uh, Also, you can prove that in GL we have the axiom of transitivity, which says as box phi in then box of phi. So we can say that GL is K4 plus the axiom of Lob. So we can say that GL is K plus the axiom Lob, or we can say that GL is K4 plus the axiom of Lob. We don't have enough time that I want to talk about Godel-Lob probability logic. If you are interested about that, you can read about it in many literature, such as the book Probability Logic by Godel. If you may remember, in c-semantics, we said that Lob formula is valid in the frame W and R if and only if R is transitive and conversely well-founded. And a relation R is well-founded if there is no infinite sequence that ends to some point, or thus we can say that the converse of R is well-founded if there is no infinite path starting from some point. So in particular, we don't have any cycle or loop. In the first session, we don't have enough time to give the proof of that, but I think today we can give a proof for that. I want to show that Lob formula defines the class of transitive and conversely well-founded frame. So first assume that F is transitive and conversely well-founded. We have to show that the Lob formula is valid on F. So suppose that F is not valid on F. By L, I mean the axiom of Lob, which says that box of P, then P, then box of P. So when some formula is not valid on F, it means that there is some model based on F and some point where this formula is not does not satisfy at that point and model. So where is evaluation? There is a model M equal to F and V and point W in W such that in M and W L is not true. So when L is not true in some points, it means that the first condition is true, but the second one is false. So W satisfies box of P, then P, but box of P is not true in W. So when box of P is not true in W, it means that W has successor W1 where P is not true. At least in one of its successor, P is not true. Also, we have that box of P, then P is true in W. So in all of its successor containing W1, box P then P is true. So box of P then P is true at W1. P is not true in W1, so box of P is not true in W1. So box of P is not true in W1, so W1 has successor W2 where P is not true. So we have W1, W2. Our frame is transitive, so we have WR, W2. Again, we have that W2 is a successor of W, so box P then P is true in W2, P is not true in W2, then box P is not true in W2, and again we can continue this argument. W2, now by repeating the argument, so we can continue this argument and from W1, W2, W3, and so on. So we found an infinite sequence. an infinite path WR, W1, R, W2, R, so on, which is contradict with non-well-founded, conversely well-founded. So if F is transitive and conversely well-founded, then the formula L is valid on F. Now suppose now for the other direction. We have to show that if L is valid on F, then F is transitive and conversely well-founded. To prove that, we use contraposition. Assume that either R is not transitive or its converse is not well-founded. We have to show that in each of these conditions, we get a contradiction. First, assume that R is not transitive. Then we have to find a valuation where L is not true. To this case, let me just set it in. If R is not transitive, we have, for example, this condition that we have W1, W2, and W3, where W1 is related to W2, W2 is related to W3, but W1 is not related to W3. In this case, just let V of P be the set of W2 and W3. Then you can make a model over F where L is not true. You can do it by yourself easily. Let's consider the other case. since it's not conversive well founded, so there is an infinite path, there is an infinite sequence, W0 or W1 or W2 or W3 and so on. Now we define evaluation V such that V of P is the set of W minus the set of all X in W such that there is an infinite path starting from S. So V is defined as follows. For example, we have point W0. It has some successors, but in at least one of the paths starting from W0, we have an infinite path. In the other one, we may have finite or infinite paths. So we set P true in the set of all points where there is no infinite path from there. So if it's finite path, P is true in here, but if it's infinite path, P is not true in each of them. Then you can see that with this valuation, with this valuation in point W0, L is not true. So in each of the case where R is not transitive or R is transitive but not conversely well founded, we can find a valuation which make L false. So if L is valid on F, so our frame is transitive or conversely well founded. It's proof that GL is complete with respect to the finite irreflexive trees, or GL is complete with respect to the class of all transitive converse well-founded frames. We have this condition. As I said, we can prove that L defines the class of transitive and conversely well-founded frames, and we can prove the completeness. And we can prove the first result because if our frame is finite and transitive and finite irreflexive, then we have the converse well-founded condition and vice versa. Because we have this theorem, by this proposition. By using this proposition, And the condition that GL is complete with respect to the class of transitive converse to well-founded frame. We can prove that GL is complete with respect to the finite irreflexive trees. One of point that we have for GL with respect to semantic is that GL is not strongly complete. What is the strong completeness? In completeness, we said that soundness and completeness, we have that if phi is a theorem, if and only if phi is valid. In a strong completeness, we said that if gamma phi is a proof of a set of formula gamma, then phi is valid over gamma. It's for the strong completeness. GL is not complete, strongly complete with respect to any class of cryptic frames. To see that, we can provide a counter example. Consider the set gamma, which is diamond of P0 union box of Pi, then diamond of Pi plus 1. Any finite subset of gamma is satisfiable. Because if gamma prime is a finite subset of gamma, then we can consider gamma prime as set which is in the form of diamond of P0 union of box of Pi, then diamond of Pi plus 1 for I less than some n. For any finite subset of that, we can consider gamma prime as this form. Now consider a model where it's in this form. We have W, W1, W2, W2, and 2W, and W1, W2, and then set V of PB equal to, for each I, V of PB, V of PI be equal to WI. So in W0, P0 is true, in W1, P1, W2, P2, to Wn we have Pn is true. Then you can see that in W, diamond of P0 is 0 is true. And also consider this frame as transitive frame. So we have it's transitive. You have to add some arrow, but as I said, just consider it as transitive frame. So in any point that P1 is true, then diamond of P2 is true. If P2 is true, then diamond of P0 is true. So it's true in this model. But gamma cannot be true in any point of a transitive conversely well-founded, model, because or we can say that, see this, suppose that gamma is true in some point W, and W is a point of M where M is transitive and conversely well-founded. Now put X be the set of all point X where X is accessible from W, and for some I, X satisfies P I. Since P0 is true in W, diamond of P0 is true in W, which means that W has at least one successor where P0 is true, we can conclude that X is non-empty. Now assume that X is some point in X. Then by definition of X is accessible from W. And we have X satisfies Pi, then diamond of Pi plus 1. Because if X is in X, there is some I where X satisfies Pi. And we know that for any successor of W, if Pi is true, then diamond of Pi plus 1 is true. So in X, we have Pi, then diamond of Pi plus 1. Thus, for some Y, we have X Ry, and Y satisfies Pi plus 1. By transitivity, you have WRX, XRY, so we have WRY, so WRY, Y satisfies Pi plus 1, so Y is in X. Therefore, each element of X goes to another element of X through Y, through R. R cannot be well found. So by starting any point from X, we have another points and go to them. So we can see that GL is not strongly complete with respect to Kripke frames. Now let's consider the topological semantics of GL. The topological space is called scattered if it has no non-empty dense in itself subset. Or equivalently, if every non-empty subset of X has an isolated point. So a topological space X is scattered if every non-empty subset of that has at least one isolated point. We can prove that a topological space X is scattered if and only for any subset y of x, we have d of y is equal to d of y minus d of y. So we have this property for any topological space. So x is scattered if and only for any y as a subset of x, we have d of y is equal to d of y minus d of y. We can prove that each scattered space is a TD space. Let's see that. So we have time to do that or not? I want to show that each scattered space is TD space. Suppose X is scattered and A is a subset of X, then D of A is a subset of D of A union D of A. It clearly true that we know that D of A is a subset of D of A union D of A, which is D of A union D of A by the properties of derivative set that we said in the beginning of this session. We know that it's true. Let B be the set of A union D of A. Then D of A intersection with D of B complement is empty. Because D of B is D of A union of D of A. And when we consider its complement, the intersection is empty. Also, since X is scattered, we have D of B is equal to D of B minus D of B, which is D of B intersection with D of B complement, which is equal to D of A union D of A intersection with D of B complement. I just put the definition of B in here. So it's D of A intersection with D of B complement, which is a subset of D of A. Therefore, we have that D of A is a subset of D of A. For TD space, we have to show that for any subset A of X, we have D of A is subset of D of A. And we prove that for scattered spaces. Then we can show that the Lob formula defines the class of scattered spaces. Let's see that. To see that, first note that the Lob formula is equivalent to this formula, diamond of P, then diamond of P, and the negation of diamond of P. We consider the diamond version of the Lob formula. Now, suppose that X is a topological space. Then X satisfies diamond of P, then diamond of P, and the negation of diamond of P if and only if D of A is a subset of D of A intersection with D of A complement for any A as a subset of X, which is equivalent to D of A is a subset of D of A minus D of A for any A as a subset of X. Since X is scattered, if and only if D of A is a subset of D of A minus D of A, which we said that it's true before for each A as a subset of X, then the claim is proved. So we show that the Lob formula defines the class of scattered topological spaces. Now we want to again prove the completeness of GL with respect to a scattered space by using the completeness of GL with respect to the appropriate class of Kripke frames. Suppose that X is a transitive irreflexive frame, then X is conversely well-founded if and only if the offset topology over X is scattered. So if I have a transitive irreflexive frame and it's also conversely well-founded when I consider its offset topology it's scattered. According to this and the completeness of GL with respect to finite transitive irreflexive frames, we can prove that GL is complete with respect to the class of scattered spaces. So we have the completeness of GL with respect to scattered spaces. Also, there is a theorem by Abashis and Blas. They proved separately, but they proved that for any ordinal alpha, which is equal or greater than omega to the power omega with the interval topology, we can see that GL is complete with respect to any ordinal alpha. We don't have any time to discuss about that, but I just want to mention that we have such interesting results about GL and ordinals. This proof is based on the following lemma, which shows that for any finite transitive reflexive tree of depth n, there is an anti-dimorphism from omega to the power n to d. We can find this proof in some literature which are about the topological semantics of GL. Also, one of the advantages of considering the topological semantics for GL is that we can have the strong completeness here. There's a paper here which proved that GL is strongly complete with respect to any alpha which is equal or greater than any omega to the power omega. We saw that GL is not complete when we work with script key frames, but when we consider topological semantics, we can have the strong completeness of GL. So it's one of the advantages of considering topological semantics for GL. Now, I think we can finish this course. I tried to give a brief introduction of topological semantics of modal logic and review some results here. I hope it was interesting for you and you want to learn more about that. If you want, you can find many interesting paper here. Thank you for participating in this course.